In this video, we're going to look at solving trigonometric equations and deciding which method is the one that can work and is the most efficient one. So let's look at our first scenario here. So we got 3 sine x plus 2 cos x equals 0. So this is a standard scenario you'd be expected to be able to solve. Now the current issue is the fact that we have multiple trig functions present. We prefer to just have an equation where there's only one trig function. So there's only sine, or there's only cosine, or there's only tan. Okay, so we need to think, what can we do to achieve that? Now, this specific scenario we're looking at is where we have sine multiplied by a numerical value. We have cosine multiplied by a numerical value. They might be added or subtracted together, but there's no other terms in the equation. You can see on the other side, we've just got 0. Okay, in this specific scenario, we're going to make use of the identity that says that tan theta is identical to sine theta over cos theta. Now, in order to make use of this, because currently we don't have any fractions in my equation, so what we're going to do is we're going to divide both sides of the equation by cosine, and it wouldn't be cos theta because the angle that we're working with is x. We're going to divide by cos x on both sides. So I'll just write it here. Now what we have to do is go through each term and divide by cos x. So we would get 3 sine x over cos x plus 2 cos x over cos x. And then on the other side, we'd have 0 divided by cos x. Now this first fraction here, this is where we can make use of the identity because we've got sine x over cos x. So I know that's going to become 3 tan x. Then in our next fraction, we have a cos x over a cos x, which will cancel. So we're just left with 2. And then on the right hand side, 0 divided by any non-zero value would just be 0. Okay, so that's not going to change. Now what we've achieved by doing this is we managed to rewrite the equation so there's only one trig function in there, which is tan. So we should now be able to solve this. Let's rearrange to get the tan x on its own. So we'd have 3 tan x is equal to negative 2. Then tan x would be equal to negative 2 over 3. And then we can use our inverse function to find x. So x is going to be equal to the inverse tan of negative 2 over 3. And then we'll put that into the calculator. Just make sure we're in degrees, as that's what we're working with in this question. And my angle for x would come out as negative 33.7 degrees. Now just check this versus the range we're trying to solve for. So we're trying to do 0 to 360. Therefore, this is not going to be a value that I want in my final answer. However, we could use it to get my correct answers. So if I was to draw a tan curve, so we'd have this part of the graph here. So this here would be 90. Okay, and then I'm going to draw another repetition on my tan curve. So this here would be 270. This would be 180. And then we want to go to 360. So I'm just going to extend this a little bit more. And then we'd have 360 there. Now the first angle we've got out is negative 33.7. So remember, angles are on your x-axis and your tan values are on your y-axis. Now negative 33.7, if over here is negative 90, then negative 33.7 should be roughly, I'll do it in a different color, it should be roughly here. So that should be negative 33.7. Now what we want to figure out is the other points which has the same y coordinate. So what you're going to do is you're going to go across horizontally at that height until you hit the curve again, which would be here. Okay, so then what I'm going to want to do is go up to my axis, and I need to know that angle there. So in order to figure out that, it's actually quite straightforward for tan, because in one repetition of your tan curve, each y coordinate only appears once. Therefore, if I want to get from this angle to the next one here, I just have to add the length of a tan curve, so a period of a tan curve, which is just 180. Okay, it repeats every 180 degrees. Therefore, if I add 180, okay, I would get 146.3 degrees to 1 decimal place. That would be a valid solution. But what I have to consider, is there any other angles which have the same y coordinate? So I'm going to keep going across horizontally. So I'm going to keep going from this point here, across here, until I hit the curve again. And I need to know, what is this angle here? Now, once again, that is on my next repetition on my tan curve in the exact same spot. So therefore, I would just need to add 180 degrees again. And I'm going to get my next value, which is going to be 326.3 degrees. So with tan, I wouldn't even bother drawing out the curve. You just need to keep adding 180 or subtracting 180 if you're trying to go to the left. So my answer should be that x is equal to 146.3 degrees and then 326.3 degrees. Okay, we would not use the negative 33.7 because it's outside of the range we're solving for. So that will be our answer to our first question. So now let's have a look at another scenario. So this is our new equation. It's very similar to the last one. If I just zoom out, we have got the exact same left-hand side. Okay, I haven't changed that. The only thing that's changed here is the 2 on the other side. We now have another term other than our ones involving our trigonometric functions, which is going to make things slightly more difficult. Because let's try the approach from before. Let's try dividing by cos x on both sides and see what happens. So I'm going to write in divide by cos x and divide by cos x. So for my first term here, if we do 3 sin x over cos x, that's going to give me 3 tan x. Then if we do 2 cos x divided by cos x, that's just going to give me 2 because the cos x's are going to cancel. But on the right hand side, and this is the step some people forget, you also need to divide the 2 by cos x. So I would get 2 over cos x. By doing that, I haven't managed to rewrite the equation as only one trigonometric function. Okay, because we've got tan x and we've got cos x. So this does not appear to be working. Okay, so dividing by cos x on both sides is not going to work because of this extra numerical value 2 that we have here. So we're going to have to use a different approach for these types of equations. And what we're going to have to make use of is the r sine or the r cosine format. Okay, so we can either write this left-hand side in the form r sine x plus some angle, or we can do r sine of x subtract some angle, or we could do r cosine of x plus some angle, or we could do r cosine of x subtract some angle. Now that angle alpha would vary for all of these. They'd all be, you'd get a different angle for each of them, even though they've used the same symbol. However, you can use any of these 4 in order to solve the equation because we're not told to use a specific one. Okay, they're all equivalent because the sine curve and the cosine curve are just translations of each other. They're horizontal translations, and the horizontal translation is represented by this angle here. So you'll just get a different angle for each of the 4, but if you were to draw all 4 curves, they'd be exactly the same. Okay, so it's completely up to you which one you're going to use. I'm just going to go with the first one I've written here, the r sine x plus alpha. Okay, so I'm going to rewrite the left-hand side of my equation in this format here. Now, in order to help us do this, we're going to make use of the formula booklet. So I've got the formula booklet here written on the side, and I've got our compound angle identities, which we're going to make use of. So to get this process started, I am going to write that 3 sin x plus 2 cos x needs to be identical to r sine x plus alpha, like that. Then what I'm going to do is I am going to expand the right-hand side using our compound angle identity. So I'm going to rewrite this part here, and we want sine, so we're going to be using this top one, and we've got a plus here, so we're going to be using the top part here. So it's going to be pluses throughout. Okay, so let's rewrite things then. So we'd have the r, and then in brackets I would get sine a, so a would be x, and then it would be cos b. So cos, and then b would be the alpha. And then we would have our plus, and then we would have cos a, so cos of x, and then we would have sine b, so sine of alpha. So essentially, for the second part, the angles just swap around. So we get this here. Then what I'm going to do next is expand the brackets. I'm going to multiply both of our two terms by r. So I would get r sine x cos alpha plus r cos x sine alpha. Like that. Now I'm also just going to carry down the 3 sine x plus 2 cos x, just for comparison purposes. And this is an identity. So what we can do is compare the left-hand side and the right-hand side, because the idea is this should be equal for all values of x. Okay, so if we look at the left-hand side, we've got 3 sine x on the left-hand side. I should be able to get 3 sine x on the right-hand side. So the question is, where is the sine x coming from? Well, if I look at my two terms, only one of them has sine x in it. Again, it's the first term here. You can see the sine x written there. So therefore, this term here should be equal to the 3 sine x. So we should get 3 sine x is equal to r sine x cos alpha. Like that. So we now have a slightly more straightforward equation. But also on the left-hand side of my identity here, I have 2 cos x. So on the right-hand side, I should also be able to get 2 cos x. If we look, where is the cos x appearing? It's over here. So therefore, this term here should be able to give me 2 cos x. So I would have 2 cos x is equal to r cos x sine alpha. Like that. So now what I can do is go to both of these equations that I've got here, and I am going to simplify, because for the first one here, the sine x is common factor of both sides. So therefore, I could divide by sine x and divide by sine x to get 3 is equal to r cos alpha. And then on the other one, I could divide by cos x and divide by cos x. And that would leave me with 2 is equal to r sine alpha. Now we have this pair of simultaneous equations in 2 variables, which I'm going to make use of. So first off, in order to find r, what I'm going to do is I'm going to square both equations. It might not be clear why yet. So I would get 9, which is 3 squared, is equal to r squared cos squared alpha. And then for this one, I would have 2 squared, which is 4, is equal to r squared sine squared alpha, like that. Now what I'm going to do next is I'm going to add my 2 equations together. So I'm going to have 9 plus 4, which gives me 13, is equal to, and there will be the r squared cos squared alpha plus the r squared sine squared alpha. Now the reason I've done this is because the right hand side should now look somewhat familiar. Okay, it should remind you of one of the other trig identities I haven't mentioned yet, the fact that cos squared theta plus sine squared theta is identical to 1. And in order to get the cos squared theta plus sine squared theta, or in this case it's going to be alpha, I'm going to factorize out my common factor of r squared. So I would have r squared, and then in brackets cos squared alpha plus sine squared alpha, like that. Then what I've got in my brackets here now matches with my identity, so I can replace the cos squared alpha plus sine squared alpha with a 1, which is what it's identical with. So I would get r squared times 1, but I don't need to write the times 1 because it's not doing anything. And therefore I can find r. R would be the square root of 13. Okay, we're just going to use the positive square root for this. So we managed to find r. What I now need to do is find alpha. So you could do that by substituting your value for r back into your equation for 1 or for 2. However, I'm going to do it a slightly different way just to demonstrate another method. What I'm going to do is I'm going to take equation 2, and I'm going to divide it by equation 1. So what I'd be doing is taking this 2 here and dividing it by this 3. So I would get 2 over 3 is equal to, and then on the other side of my equation, I would be doing the r sine alpha divided by the r cosine alpha. So r sine alpha divided by r cosine alpha. Now the reason I've done this is so I've only got one trig function and I'm not going to have r anymore. Because in that fraction on the right hand side, the r's are going to cancel. So we're just left with sine alpha over cos alpha, which is equal to tan alpha. So then we can figure out what alpha is actually going to be by using our inverse function. So we're going to do the inverse tan of 2/3. So then my value for alpha would come out as 33.7 degrees to 3 significant figures. So we've now managed to find our angle, so I can now substitute all the information I found into my r sine format, which is written at the top here. Okay, that 3 sine x plus 2 cos x is equal to r, which is root 13, and then it would be sine bracket x, and then plus our angle for alpha, which is the 33.7 degrees, like that. And if we look back at the equation we are solving, this should be equal to 2. So I'm going to write the equal to in here. And then you can see I've ended up with an equation with just one trig function in it. So we now should be able to solve. So we're going to get the sine function on its own. So I'm going to divide by root 13 on both sides. So I would get our trig function there. And then that's going to be equal to 2 over root 13. And now we can use our inverse function. So x plus 33.7 is going to be equal to the inverse sine of 2 over root 13. So that gives me 33.7 degrees. But now what we have to do is just consider the range that we are working in. So the range we are working in that was requested by the question is 0 to 360. So I'm just going to write that over here. However, if we look at the angle in our trig function, it's x plus 33.7. Therefore, the initial angles we find before we subtract the 33.7, okay, is going to be a different range to the 0 to 360. So what I'm going to do is I'm going to go to this inequality. Instead of having x here, I need to have x plus 33.7. So I'm going to add 33.7 like that. And therefore, I need to add 33.7 to the 0, which gives me 33.7. And then I have to add it to the 360, which is going to give me 393.7 like that. Okay, and the initial angles I'm finding have to be between 33.7 degrees and 393.7 degrees, so that when I subtract away 33.7, we'll get our 0 to 360. So if we look at the angle we found so far, we've got 33.7. That one's fine. But what I now have to do is use your cast diagram or your graph to find some other angles within our range of 33.7 to 393.7. Okay, so I'm going to draw our sine curve. So we're doing sine because that was our trig function here. So if I draw it out, and we're interested in the positive angles, I'm just going to go that far. So we got 0, we got 180, we got 360, and in the middle here would be 450. So we're not going to be going beyond here with what I've drawn, because we're only going up to 393.7 degrees. Now, if we look at the angle we've got so far, we've got 33.7. Now, this middle pot here is 90, so 33.7, if I do it in a different color, should be roughly over here. So what I'm looking for is angles which give the same y coordinate. So to find that, I need the same y coordinate, so I need to go across horizontally. So I would hit the curve here, and if I keep going, I would also hit the curve over here. So I've got this angle here I need to know, and then I've also got this angle down here but I also need to be able to calculate. Okay, so for this first one here, the idea is this gap here, 33.7, is equal to this gap here. Okay, so therefore I would need to do 180 subtract 33.7, which would give me 146.3 degrees. And then for the angle over here on the right, well, this gap in here should be the same as the 33.7. So I would need to do 360 plus 33.7. And that would give me 393.7, which is indeed within my range here. It's right on the limit. Okay, so I need to use those angles. So what I'm going to do is go back to here, and next to the 33.7, I'm going to write 146.3 degrees and 393.7 degrees, like that. Okay, and those are going to be used to help find my final solutions for x, which I'm going to obtain by subtracting 33.7. So if I subtract 33.7 off this value here, I'm going to get 0 degrees, which is a valid solution. It is an angle. And then for our next one, if we do 146.3 subtract 33.7, I would get 112.6 degrees to 1 decimal place. And then let's do the 393.7 subtract the 33.7, and that would give me 360 degrees. So those there would be my 3 solutions to that trig equation. Okay, so this one here does look a bit more complicated because initially our angle is no longer just x, it's now 30 plus x, but importantly it's 30 plus x on both sides, okay, in both trig functions. Okay, which is going to be quite important when we use identities, because the identities that we've mentioned in this video all require the angle to be the same. Now, the actual format of this equation is some numerical value 5 times a function of sine, and then a numerical value 3 times a function of cosine, and there are no other terms added or subtracted. So this format here very closely resembles the very first equation I did at the start. Okay, which was one where we had it equals to 0. If I wanted equals to 0, I could just put this term on the other side. Therefore, I can use the same approach that I used in that very first question, which was to make use of the fact that tan theta is identical to sine theta over cosine theta. Now, this identity works providing the angles are the same, which they are, because they're both 30 plus x. So I'm not going to divide by cos x on both sides. I'm instead going to divide by cos of 30 plus x, because that's my angle, like this. So what's going to happen on the left-hand side? The sine 30 plus x divided by the cosine 30 plus x gives tan 30 plus x. But don't forget about our 5 in front. And on the right-hand side, the cos 30 plus x cancels with the cos 30 plus x, so we're just left with 3. So now we have an equation with only one trig function in it, and that is tan. So now we can rearrange to get tan on its own. So tan 30 plus x is equal to 3/5. So then we're going to use our inverse function. So we would get 30 plus x is equal to the inverse tan of 3/5. And if I do the inverse tan of 3/5, I get 31.0 degrees to 3 significant figures. Now, it's at this point you should be using your cast diagram or your graph to obtain your other angles. However, I did speak earlier in the video that if we have tan, you just need to add or subtract 180. So I'm not going to draw out a graph to do this. But what I do need to do is just consider my range, which is 0 to 360. Because inside my tan function, I have 30 plus x. So I need to go to my inequality and add 30 throughout. So I would get 30 plus x in the middle, and then you'd get 0 plus 30 gives me 30, 360 plus 30 gives me 390, like that. So initially I'm looking from 30 to 390. So let's go to the 31.0 and we're going to add 180 to it. So I'm going to get 211.0 degrees. And then if we add 180 again, we're then going to go beyond 390. I'm actually going to get 391 degrees. So therefore, I'm not going to go any further. I'm just going to leave it as those two. Now, subtracting 180 is not going to help with the 31 because that's going to take me into negative angles, which is not in my range. So now we can find x by subtracting 30 off both of these angles. So I am going to get 0.964 degrees when I subtract 30. Just remember, this value here is a rounded value. That's why it's not come out as just 1 degrees, okay, because I've got it stored in my calculator. And then for the 211, if I subtract 30 off that, I would get 181 degrees to 3 significant figures. So those there would be my solutions, which both fall within the 0 to 360 range. Just double check that. Let's have a look at my next scenario. So this scenario looks very similar to the previous one. Okay, if I just scroll up and have a look at that one, you can see we have a 5 sine and a 3 cosine, which is exactly what we have down here. However, the difference between this one and the previous one is the fact that we have 30 plus x in this bracket, but 30 minus x in this bracket. So the angles are different. Now, what that means is we will not be able to use the fact that tan theta is identical to sine theta over cos theta, because for this identity to work, all the angles have to be the same. So we're going to have to use a different method. So I don't like the fact that the angles are different, so I want to change that. So I need to think, well, what could I potentially use? Now, given that there's a plus and a subtract in our angles, there's something that we already mentioned in this video that could be helpful, and that is the compound angle formulae. So I've got them here. Now, if we look at our right-hand side, we have sine, and in the middle, we got a plus, okay? So therefore, we would be using the top one here, and we would be using the plus part, which is the top part here and here. Okay, so our value for A, we can say is 30, and our value for B is going to be x. So don't forget about your 5. So I'd probably just write that out first and open your brackets. And it's going to be, if we do our first term, so sine A, which is 30, and then cos B, which is x. And then for our next term, it's cos A sine B, so it's going to be plus, and then cos 30, and then it's going to be sine x. Close bracket. Now let's move on to our right-hand side. So I'm going to write equals 2, and then we got our 3, and then open brackets. Now if we look at our right-hand side, we're going to have to use cosine. So therefore we would be using the bottom one here, and it's subtract. So we'll be using the bottom strand, which is a subtract there, and then it's a plus there. Okay, so our A would be our 30, and then our X would be our B. So if we do our first term, it's cos A, cos B, so it's going to be cos 30, and then cos X, and then it's going to be plus, and then it's going to be sine of both of our two angles. So sine 30, and then sine X, like that. Okay, so we've successfully used our compound angle formulae. Now we're going to have to think about what we're going to do with this, because it actually looks more complicated. However, now, if you look at our angles which are unknown or have unknowns in them, we've got cos x over here, we got sine x, we got cos x, and we got sine x. They all have the same angle, whereas all the other trig functions we've got there have a numerical angle in it, so therefore we could actually find what they are, and actually sine 30 and cos 30, these are exact values. You can get these out your calculator if you know them from memory. So that's what I'm going to do next. I'm going to go through and I'm going to rewrite all our numerical ones as their exact values. So first off, we have sine 30. So that is a half. And then we got cos x. And then we got cos 30, which is root 3 over 2. Then we got sine x, close bracket. And then over here we got 3 lots of, and then cos 30 again, which is root 3 over 2. And then cos x. and then plus, and we got sine 30, which was a half, and then sine x, like that. Okay, so it's beginning to look a little bit more simple. What I'm going to do next is expand the brackets, just so the equation's a bit more flexible in terms of rearranging. So I would have 5 over 2 cos x plus 5 root 3 over 2 sine x is equal to 3 root 3 over 2 cos x, and then plus 3 over 2 sine x. Now that we got this far, it's still not looking that simple that I can easily solve it. But the fact that we have cos x over here and cos x here makes me think I want to get them together. And the same with the sine x's and the sine x's. Okay, I want to essentially collect like terms. So what I'm going to do is I'm going to move our cosine terms to the left-hand side and our sine terms to the right-hand side. So we're going to leave the 5 over 2 cos x where it is. But I'm going to subtract the 3 root 3 over 2 cos x. So I'd get subtract 3 root 3 over 2 cos x. Then we have equals to, and we're going to leave the 3 over 2 sine x on this side. But what I'm going to do is subtract this term to the other side. So we get subtract 5 root 3 over 2 sine x. So on each side, we now only have one trig function. How they still appear twice, but on each side, the trig function is a common factor. So I'm going to factorize it out. So on the left-hand side, I'm going to write cos x, and then in brackets, I would have 5 over 2, take away 3 root 3 over 2, like that. And on the right-hand side, sine x is my common factor. Then in brackets, 3 over 2, subtract 5 root 3 over 2, like that. We've now isolated our trig functions. Now what we can do is relate this scenario back to the very first question we had up here, okay, because essentially we've ended up with the same scenario of a numerical value times sine and then a numerical value times cos and no other terms. So if I scroll down and look at our equation, our numerical value is this entire bracket on each side. And then we've got the cos x and the sine x multiplying them. So what I'm going to do next is I'm going to divide by cos x on both sides. So on the left-hand side, if we have cos x over cos x, that's just going to become 1. So we're just left with my brackets, which is 5 over 2, subtract 3 root 3 over 2 is equal to, and on my right-hand side, the sine x divided by cos x is tan x. And then in brackets, multiplying it, I'd have 3 over 2, take 5 root 3 over 2, like that. Then I've got one trig function, so I want to get the tan x on its own. So I'm going to divide by my brackets here. So I would get the 5 over 2, take 3 root 3 over 2 on this side already, which is my numerator, divided by what I circled there. So the 3 over 2, subtract 5 root 3 over 2 is equal to tan x. Now we can use our inverse function to find x. So I'm going to put it in the calculator. And I would get 1.98 degrees as my first angle, my principal value out of the calculator. And because it's tan, we said we could just add or subtract 180. Now our range in the question, I believe, was 0 to 360. So I'm just going to add 180 to this value. So I'd get 182 degrees to 3 significant figures. And then if we add 180 again, I actually go beyond 360. So therefore, these two here would be my angles and my solutions to the equation.